Welcome to myprojectbuzzer.com. We are going to see the product for optimized built-in self-repair for multiple memories. Next we are going to see the abstract for our product. Today's deep background technologies allow the implementation of multiple memories on a single chip. Due to their high density, memories are more prone to faults. These faults impact the total chip yield. One way to solve this problem is to enhance the memory by redundant memory locations. The address mapping of the fault-free working memory is programmable within certain limits. In order to do so, a memory test is named to identify the faulty regions. The memory is tested by external test hardware or by on-chip dedicated hardware. Example, memory BIST. The second testing strategy is the preferred method for embedded memories. After memory testing, the memory address map is programmed by means of volatile or non-volatile storage on or off chip. To provide the test pattern from a memory BIST, a multiplexer in front of the memory is widely used. Redundant spare rows and spare columns are often included into the memory. This impacts the performance and area condition of the memory. The memory is repaired during testing by storing faulty addresses in registers. These addresses can be streamed out after test completion. The application can be started immediately after the memory BIST process. The redundancy logic calculation will not increase the test time of the memory BIST. The memory BI as a concept contains an interface between memory BIST logic and a redundancy wrapper for storing faulty addresses. There are various BISR schemes for multiple memories because routing, timing and power consumption are realistically considered. Next we are going to see the flow diagram for our product. In this flow diagram, the BIST unit and the BIRA unit are the important factors. The BIST detects if there is any error in the memories. The BIRA unit search for the redundancy memory cells and repair the faulty cells. When the fault is detected by BIST, the fault information is sent to BIRA through the port fault_info. After the test is completed or stopped, the signal test_finish is activated and BIRA executes the RA process to find repair solutions. The BIST unit consists of test pattern generator, test address generator and the controller. The built-in redundancy analysis unit consists of counter, multi-fault detector, fault storing, content addressable memories and the repair registers with the CTR. In the BIRA unit, the notations are defined as follows. M is the number of rows of memory and N is the number of columns of memory. The fault storing cams are classified into two cams. The enable flag is used to recognize the valid information. When the signal test start is asserted, TAG and TPG generate test patterns and test addresses for executing the adapted merge test algorithm. The overall test procedure is controlled by the signal test control. The clock and reset signals are provided through clock and reset. The CMP compares the results from the memory and expected responses to detect faults. If a fault is detected on the largest memory, the fault information is sent to BIST through the port fault_info. Because memory can be repaired by BIRA sequentially, if the largest memory is faulty, the faulty information is sent to BIRA during the parallel test. The BIRA search for the redundancy cells and repair the faulty cells. Finally, we are going to see the output for our product. We write the code in VHDL and we see the output in the Xilinx 14.2. Double click on the software. The software will be opened shortly. The software is opened. Here we read the code. To create a new project, click on File and then click on the New Project and specify the folder to which you want to save your code, project and new source for the program space. To simulate the program, we have to click on Simulation and then on the main icon and then on the Simulate Behavioral Model. We will see the simulation in the iSim. We have to give the inputs from where it is mentioned. The simulations is based on the inputs and the expected output will be shown. The simulation is done. Here you have to give the inputs. The inputs are clock and reset. Go to force constant. Give the value as 1. Then for the clock you have to give the force clock and leading edge value is 0 and the trailing edge value is 1 and the period is 1000 nanoseconds. Click on apply and then OK. Whether you have to click the above mentioned position or you can enter the enter option. Then click on the run. If there is any error, the output will be 1 and it is repaired and the status will be shown as 1. Then click on the reset and then give the value as 0. Then click on the run option. The address which holds the data is compared in the list for default and if there is any error occurs, it will be given to the BARA and the repair will be corrected. Minimize the iSim. We can see the implementation results by clicking on the implement and right click on the implement design and run. Here the implementation process is completed. Then for the synthesis report, click on the synthesis report and we can see the number of flip-flops, number of LUTs used for this product. These details will be given here. Number of latches and number of edges also given. Then for the timing report, click on the timing report. Then for the delay purpose, you can see the delay values as 4.923 nanoseconds. Then for the synthesis XST, we click on the view RTL schematic, then OK, and click on add and create schematic. We can get the technology diagram. Thank you.